lead for control systems engineering group, having design, configuration management, and security responsibilities for several INL nuclear facilities and various control system architectures. Welcome, Dr. Rieger.
Well, thank you. And so what that summarizes down to in a sentence or two is the fact that the first part of my life was as a process control engineer on non-reactor nuclear facilities. We did a lot of control system additions in the 80s into the 2000 era. Crossing over with that, I went back for my PhD, had a very distinguished advisor, Professor Suvaram Naidu, who's not at Idaho State University anymore. He is in the Midwest, but well known in control system circles. And the interesting thing is that I rarely get to work anymore with process systems. I still, of course, think that because early work, but mostly thinking power systems. And I'm definitely not a power engineer. I would profess that I'm a electrical engineer, if you wanted to put it in discipline, at least relative to my PhD, but it's specifically controls. But INL is, we cross many domains, but power is the big one. And so the systems I have include, multiple copies of Opal RT, we've got RTDS systems, etc. So you have to pick a domain, and power happens to be the nice one, as much as I would like to work with chemical plants and things like that once in a while too. So what I'm going to be talking about today really overlap the CyberPhysical research area. In my history with the lab, about 2008, I took over what they called a signature area. So for those of you that know laboratory directed research and development, which is a way for national labs and other federal agencies to be able to kind of direct their own research as compared to being tied to a specific scope from a customer. They had what they called these signature areas, and there was various numbers when Battelle took over the contract, but I came into one of those. They have 3 directorates at INL. One's National Homeland Security, which I'm part of. They also have the Nuclear Science and Technology, and they also have Energy and Environment. Each one of those stewarded one of these signature areas, and the intent was to take an existing capability and expand its recognition. The one I was over, Instrumentation, Control, and Intelligence Systems, and that cool looking head in the middle of my slide was a symbol for that. Officially, it's not a logo because it's not simple enough, but anyhow, it's the one that ran the longest. We brought in people from all 3 directorates: cognitive psychologists, control engineers, cybersecurity scientists and engineers, to think about what does resilient control systems mean. So when you go out and do a search on the Wikipedia for resilient control systems, that's one I wrote based upon working with my team a decade or so ago. And so that's an area that's now been accepted. I see individuals in other countries setting up new workshops in resilient control systems that I wasn't even aware of until somebody sent an IEEE notice across my desk, and it's like, wow, that's really cool. It does say that there's a broad perspective that needs to go into that to really achieve resilience. So what I'm going to talk about today is getting into some of my particular research in that area, but please note that it's a research area for the community now and has been since the beginning. So what are resilient control systems? So just to kind of put a perspective, I'm going to talk about control systems and cyber systems and cognitive systems, because each one of those is a complexity. So the fortunate thing in my life is I got to do many things as a practitioner. And so nothing like understanding what the challenges are when you're dealing with them from day to day. So from a control system perspective standpoint, yes, my background's basically control system engineering. We would put a lot of pieces together. Sometimes there are different control systems, different vintages, because we don't want to update the old ones because that costs money. Sometimes it's tying to another control system, which is what we've done, another control system run by another group, because they control like a ventilation system, a supply blower. Well, we have the discharge blower on our side, they had the supply blower. Well, if the discharge blower goes down because we want to maintain vacuum, we want the supply blower to shut down, and we don't want to have an operator do that. You know, it depends on an operator. Okay, so we put in an interlock, boom, shuts it down when we want to. Well, what happens when they do a calibration of the pressure transmitter, which is what keys that interlock, and they forget to take the interlock out of effect, and all of a sudden they shut down the supply blower and they didn't want to. Well, that's just a simple expression. That problem was not actually a big one if it happened, but as you get more and more of these complexities, drawings are never perfect. People forget about things. You can put stuff in procedures, but the more complexity you put into the system, the bigger the challenges for resilience. And so even though the word distributed control systems has been around for a long, long time, they really weren't distributed. They just, you know, you'd place the interface cabinet where you wanted to, but not truly distributed, not necessarily the way you would want them to be, which is, from a resilience standpoint, you really need to minimize these interdependencies, because the more dependencies, interdependencies you have, the more opportunity to not recognize something. And in the power grid, where you have wide area as compared to distributed controls, these things can be exhibited in cascading failures. You have combinations of software failures and other things, and all of a sudden you end up with an unrecognized situation. The cognitive folks like to talk about the Swiss cheese model, where all of a sudden you may have multiple barriers in the slices, but all of a sudden the holes line up and boom, you've got a problem. So cyber attacks, we know they're increasing. The availability of tools is constantly evolving. The tools themselves build upon each other, going from initial, maybe primitive tools to modular or automated tools, things that include AI and bots. The same kinds of things we use to defend them are in the tools. So what are you going to do? You know, depending upon just a human, and understand, I think a human is still an important part of the situation. I'll talk about that with next slide. You know, the human's important, but the human can only respond in a certain time scale. If you don't go to autonomous recognition and response, a feedback loop, as we call it in the control world, but doing it in the cyber, we're in trouble. You really need to get to something that is much quicker, much better, of course, at recognition, but much quicker at responding. You also need to start thinking about the attacker as a human. Even if they develop a bot, it was developed by a human, how do you defeat the bot? So moving target defenses, things that can deceive. Okay, we don't have one option, we've got 15 options, I have to figure out the right one, or guess what? The chances of getting caught by our autonomy or a human using an orchestrator is going to be higher. We have been setting up the humans for failure for a long time. Trust me, I've done many, many control system graphics. We even had the operators build them in the first place. The more complexity we put within the system, we have to have, you know, we've had tech standards, which are very critical kinds of things, very important to monitor. I'm not saying these are my screens, because they're not. These are not ones I built, but we got multiple alarms showing up, all meaning one thing. We did smart alarming in the past to try to prevent that. In other words, one alarm per situation, not 15 alarms saying, just do this one thing. But you can see the overload that you're creating for the human. Now imagine that with cyber. And with security information event management, same situation. And part of the bigger challenge is you've got people working on cyber that can affect a control system, and you've got people working on the control system itself that have no information on cyber. So if they see a problem, oh, it's got to be physical, because that's all we have information for, that's all we know. As I'll talk later, my focus is to make the humans work more effectively, not only within their discipline, but across roles. So resilient control system, we always talked about in the early days, and actually still with a lot of people coming on board with the resilience word. What's the difference between resilience and reliability? Well, for us, resilience is about the unexpected. Could be damaging storms, a cyber attack, multiple vectors, things like that, that are not well codified in traditional reliability terms. Very high confidence probabilities or something that's first principles. We split the research in two areas: state awareness, essential knowledge to fully characterize the decision space, which is cyber and physical. You have to have both. And then resilient design, building an adaptive capacity, immune to response to threats that are not necessarily well characterized. So how do you build that into the system? It's not that ideas such as reliability go away, but how you respond may be different. How do you characterize trust? Right now, every control system out there assumes trust, right? Well, it's contested space. Can we do that? Resilient control systems is moving beyond the traditional. So in a definition, it's the capacity of the control system to maintain state awareness. I know the state of my system. I may not know how that storm is going to affect me, but I know what happened to my system so I can appropriately respond as a combination of autonomous and human response. So to maintain state awareness and accepted level of operational normalcy in response to disturbances, including threats of an unexpected and malicious nature. So that's the definition that's out on the Wikipedia, papers we've got, etc., relative to this particular environment. I will say we were the first to really coin it in the way we've said it. But there's an individual that is a control engineer that I think actually beat us to the punch. But the focus there is really kind of an evolution of optimal control. And so very control system centric, doesn't consider the cognitive, doesn't consider the cyber. And I believe as a phrase, resilient control system, it's going forward more in line with what I'm talking about today. So let's look at cyber-physical degradation, assessment, and visualization. So we need to understand what went wrong. So I've got projects that are looking at this specific thing. One of them is with the solar office right now, where we're actually looking at understanding both the physical and the cyber. And we actually, on the cyber side, ingest the physical data too. So we may see an attack propagate in the cyber world that gets revealed in the physical world if we don't catch it quick enough. I mean, the point we're trying to get to is short time scale responses. The problem when doing that in the control system world is, okay, what if you do that and create a worse problem? And I'll talk more about that later. But understanding this awareness, and from a distributed standpoint, doesn't mean there isn't a centralized orchestrator, but the time scales are short at the endpoints, and the endpoints are where the commands to the field come or go to, and monitoring comes from. If you haven't stopped it once it's gotten to that point, you're in real trouble. Ideally, perimeter protection stop most things, but we believe in distributed control here again because it can be faster and it ingests both the cyber and the physical side. Visualization, also part of the same solar project. Now, this is the original concept we had actually years ago. We've come up with simpler implementations. We call it a triad, cyber, physical, and resilience triad. So we have an initial indicator for an operator that they see on the overview. Okay, what's the root cause? And how's it affected me? What's the confidence in that? And then you can mouse over to get more specific information. You can do drill downs into screens that are role-based. We're thinking about that integration of individuals, but also quick recognition of what's wrong. Why? Because time is of the essence. What is the response and who's the main responder? If it's a cyber attack, there may be things that the dispatcher wants to do on the physical side. However, you need to mitigate the cyber attack, and there's a cyber defender for that. Cyber defenders don't necessarily know what's consequential to the physical side, the power system. And on the power system side, they really don't care about IP addresses and that kind of information. We need to bring the roles together. They need to be effective if we're looking to actually position ourselves for appropriate response. And that doesn't mean that I still don't, of course, as I've said, not want to go to autonomous systems. I think the responses need to move to autonomy. But there's challenges with it. And full autonomy is probably not going to be achieved in my lifetime, but that's where we need to go. So cyber feedback and orchestration, as I've said, looking at the real feedback loop for systems. And there's a cyber feedback loop, like there's a physical feedback loop. We've been doing physical feedback loops for over a century. What does the cyber feedback loop look like? Still involves analytics to achieve some kind of response. That disturbance can happen at many places. And then the responders are role-based. The things that you want to think about in implementing these kinds of things really relate to how you even design your networks. So let's say you're using a software-defined network switch and you want to shut off communications between a couple of segments. Well, if you're passing monitoring data from one side of the segment to the other side of the segment that had a controller on it, a feedback controller on it, well, you've just created an instability potentially because you've shut that off because you thought that was a great mitigation. So you first need to understand what's the benefit of the different cyber mitigation options, and then what's the effect. And preliminary to that, you need to design your networks so that you know you haven't put yourself in a bad position when you start launching mitigations. And although recognition is not perfect, you understand that in some of the mitigations you take. Well, if I take this mitigation, there's really no downside. I'm not going to affect much of the operations, but there's very much an upside because I think I'm going to stop, remove the connection to the remote access Trojan, and they won't have a command and control anymore. So we're going to cut it off. Those kinds of trade-offs need to be understood before full acceptance of any kind of cyber autonomy is going to happen. Moving to target defense could be based upon the understanding that you have something that keys it to happen. So you're wanting to modify the environment and how obscure it becomes. Packet payloads may look different. Things that you're modifying and how things would look from the normal, so it confuses the malicious actor or their bot. Or it could be just random. So strictly deception. It's all about confusing who's coming at you or what they're sending at you. Now, automated vulnerability assessment is just our name for a DHS project that I had, but there's other people that are doing similar kinds of things. The basic thing is being able to footprint your control systems in a virtualized space so that you can then start looking for vulnerabilities, and you can run them as multiple experiments using this virtualization. It's very easy. Since it's virtualized, you don't have to have all the equipment or the various different combinations and configurations in one place, and you can do that assessment. You can look for zero-day vulnerabilities in addition to known vulnerabilities that you run against the system. So Sandia's got their Scepter virtualized environment. This one was leveraging some of the work by Lockheed relative to the DHS project and Draper. They were both part of the team that was INL led relative to this technology. The National Cyber Range actually uses the base technology down in Florida to do these kinds of evaluations to really understand what's going on within the system. The more situational awareness for industrial control systems, which is actually a meeting I was just on before joining this one, has developed a prototype. And that prototype is focused on commercial off-the-shelf technologies, but it does include some new technologies. The new technologies look at things like the control system configuration, because one of the keys to noticing an anomaly are things changing in the configuration that shouldn't be changing. It still includes what you would consider traditional intrusion detection system, both network and host-based intrusion detection system. It includes analytical solutions, primarily outside of the analytics that are put into the individual IDSs. And yes, they have companies that are focusing on industrial control system protocols and things with their IDSs, but primarily centralized analytics in this case, The future of systems is looking at distributed analytics, right down to the individual segment, visualization of these kinds of things, and information sharing. Information sharing is in many ways, even though sticks and taxi, which is the methodology Modern first came up with, is out there to represent and transport the indicators for control systems. There's context and other things, and then how do you use it? So there's a lot of challenges still and necessity to continue to evolve beyond what we currently do within control system security. I wanted to talk a little bit about resilience metrics. This is the disturbance and impact resilience curve. There's other people that have done similar things. Normally there's a trough. Sometimes there's a hill, you know, that they want to talk about them. We have diamonds here: recon, resist, respond, recover, restore. Other people call them a little bit different. But the context for us is we're considering control systems. So more on the left, the very fast time scale. If something was affected, it's on the right, longer time scale. But the point is, when you've got cognitive, you've got cyber, you've got physical, how do you integrate them, normalize them going forward? And so we consider that time and data. You know, if you have a physical disturbance, you could have some odd configuration changes that messes up a whole network, slows it down, which I've actually had happen before in my practitioner experience. Data integrity, you have signals, transmitters that fail, cyber, you've got denial of service, you've got issues with data injection, cognitive, operator responds too slow or incorrectly. But time and data are the two primary concerns. The point is, we're wanting to develop a system that recognizes, here again, state awareness, and starts responding, automated response, cyber and physical, in a way in which when things happen, the system is adapting immediately. And we're trying to stay above that minimum normalcy. What are the critical functions that we have to keep going? We see this generally as a manifold. So manifold is just a nice mathematical way of thinking about it. You know, there's a mathematical fidelity that you can put with these kinds of things. I'll show you an application here in a sec, but basically, what's your adaptive capacity? So what level of a buffer do you have? And within that, even if you've got some degradation in your system, what's your margin to maneuver, which is really kind of an amount. So if it was generation versus loads, and also time, how quickly do you have to respond before your power system becomes unstable? We start at the physical layer, even though we consider cyber. Why? The physical, you can measure it, you understand it. You start talking about delays in a control system network. Yes, no control system engineer out there likes that. But it really starts affecting you when it starts achieving the same order of magnitude as your minimum control loops, and you start going unstable and problems start occurring. If you recognize it faster than that and mitigate it, you may not even see it. The point is you recognize and mitigated it quickly enough. But the context is the physical system, the physical dynamics. And then you work from there back to, okay, what's the cyber impact to me? What's the human impact to me? And so that's the starting point, because we can measure it and people understand it. Relative to resilience metrics, we've got the power distribution designing for resilience, or powder tool, that's out there. There's other people that are proposing different metrics. Some are small moves from, you know, what I would consider traditional operational quality of service metrics, SAIDI and SAFE, that are out there for the power system, but there's lots of different things being proposed. It's really escalating what metrics people are proposing. There are no standards that I'm aware of, just lots of proposals. In our case, what we do is based upon the swing equation. For those of you that are double E's, the swing equation, we develop the contribution of each individual asset, which could both be generation or demand response. And we align those in polar coordinates to develop the manifold that you see there. And so we can start looking at real and reactive power over time and how it's affected. And we've got tools that'll actually split that to look at ramp rates, focus more on, you know, reactive power controls, and things like that to do the analysis. And relative to the solar project in particular that I mentioned, we've actually integrated this into a visualization. So the operating engineer role would actually see a visualization of this that they can dynamically take a look at to start evaluating, their system. It's not something a dispatcher would look at. Dispatcher's looking at, just overall impacts and how they would then dispatch a line crew. By the way, that tool is open source and we're continuing to enhance that. So if you have interest, I can point you to it. You can go out to the INL open source area. So just to kind of conclude things, these are the areas of research that I work in. Upper right, I definitely consider enabling the human, not putting in a disadvantage, but getting them between roles to be cooperative with each other. Lower right, understanding the health of your system and what's impacted it as the judge for where you need to go. Lower left, the future. What does the distributed control system look like? A multi-agent system. Management, orchestration, and execution. I've got a paper out there, it's a number of years old now, that talks about this. The top two tiers are more human-based. So managerial, setting context, like for a power grid, what's the economics of the situation? What are the efficiency constraints? Central layer coordination, more of a power engineer, subject matter expert. How do we want to modify, if we're going to be losing assets, how do we want to vary the system? The trajectory is very important in how we align it, especially for wide area systems. But it's very much human, more event-based, as compared to the very bottom layer, the execution layer, which is all about time-based control, but I would consider it more supervisory control. So I see that as the future. Where we need to go, we're a long ways from it, but that's where we need to be. And we consider within that architecture, levels of pseudo-autonomy, just like you have within military commands. You have a certain set of instructions. You can operate within those instructions. You don't always have to be communicating with the command. What if you lose that connection? Doesn't mean you always want to be there, but you're now distributing the autonomy for the system. Upper left, we worked with RF hacking and other kinds of wireless protections. They affect deterministic systems. The companies are dealing with that, actually, because you can't always maintain determinism, but we consider them cyber. And then for a colleague of mine, Ryan Haruska, he's got interdependency models that he looks at the cross domains and the CyberPhysical. One final slide. This is actually referencing last year's Resilience Week. 13th year of Resilience Week. It was virtual this last year, as most everything in this arena was. For this coming year, we're actually transitioning Resilience Week. It used to be just an INL funded thing, even though many labs are involved in leadership of it. It was underwritten. Basically, the main sponsor was INL. Going into this year, we're actually looking at being tied to another organization. And so they run the logistics and things and provide us the space, and we fill out the program plan. We're looking at that being near DC, so that'll be in the October arena going forward.